So what I want to do today is we're going to be finishing chapter 2 today. We're going to talk about some more calculations, normal distribution, and then assessing normality, as they say. And those are the last two topics. We've already kind of dipped our toe into doing distribution, normal distribution calculations. We're going to finish that up today. And what I want to do is I've got 3 example problems that I'm going to work through. And kind of as I'm working through them, I'm going to talk out loud and think out loud about what I'm doing and why I'm doing it, to try and fill in those gaps of how to do these types of problems that you guys might be running into from the discussion board from last week, and to just make a little bit more sense of this stuff. So as usual, if you have any questions or comments or concerns, you need clarification, please just put it in the chat. Raise your hand, just unmute and chat out and say, hey, yo, Mr. Mosley, can you slow down, or something to that effect, or can you explain this? And I will do that. So let's get started. Let's get my pens out. All right. So as our heading says, we can answer questions about area and any normal distribution by standardizing and using table A or using technology, our TI-84 graphing calculator. Here are some examples. So I'm going to show you how to use table A and the graphing calculator today in the lesson. So we'll have those things. So on the driving range, wait, why is my, oh no, my little pen thing's on the wrong screen. Give me a second. That's not supposed to happen. Where is it? Where is it? No, where's my... Shoot. All right, there you go. The application for my little writing tablet closed and then decided not to work. Yeah. Okay. There we go. Crisis averted. All right. Hey, there we go. Now I have a pen. All right. So on the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. Suppose that when Tiger hits his driver, the distance the ball travels follows a normal distribution with mean 304 yards. And then we have a standard deviation of 8 yards. We want to know what percent, so we're going to convert whatever proportion we find to a percentage. And Tiger's drives travel at least 290 yards. This at least 290 yards means 290 yards or more. All right. We got to be careful with at least, less than, at most. Those types of verbiage things mean something important for math. We're doing at least 290 yards. That means 290 yards or more. So we got our normal curve here with our mean and standard deviations already labeled. And we have our notation here for that right here. So 290 yards, probably going to be about right here, give or take. And again, this is just for reference. All right, we have 290 yards here. Since I want to know what is more than, greater than that, I'm looking to the right. I want the area under the curve to the right. Remember, the proportion I find on table A will give me what's to the left. So whatever I find, right, I'm going to have to subtract from 1 or from 100% to get what's to the right. So our first step is to standardize 290 yards. So we use our formula for calculating Z. Say, okay, well, Z is going to equal 290 minus 304 divided by 8. This will give me a negative 14 over 8, the negative 1.75. All right, so now this is the z-score that I'm going to use on table A. All right, now the z-score is going to tell me what this proportion is. Which is why I need to subtract it from 100 to get the blue proportion. Okay, so we'll get our table A out here. Hey, look at that. I've used this already today. So we get first the negative 1.7, kind of the root part of the z-score. And the second decimal is the 5, and we find that over on the top row. We follow that into where those two things intersect, and we get 0.0401. All right, so that is the proportion of area under the curve to the left of negative 1.75. So we get 0.0401. Right, that's this thing over here. 100 or 1 minus 0.0401 will give me the proportion in blue, which is going to be 96.99. 0.9699. Right? So that is this rest of the area, right? Everything from here over 0.9699, which makes sense. When I add those two numbers together, I get 1. And that has to be the area under the curve. So then we have, as our final solution, because we need a percentage, 96.99% of Tigers drives are at least 290 yards. And we've answered the question. All right. Now, everything kind of makes sense, right? The proportion to the right should be rather large compared to the entire proportion, right? The z-score is negative. Again, that makes sense because 290 is to the left of the mean on our number line, which means it's negative standard deviations away. So all these things make sense. It all fits properly. So that's good. We want to ask ourselves, does this answer fit my drawing? Does it fit the situation? Does that make sense? Yes, it does. The other thing we can do now is we can check our work, which I can do using my calculator. Let's get out of there. Let's get out of there. So I can use my calculator in place of using table A, as long as we use it properly. And so what you do is hit second, it's bigger, second, and then the button that says VARS. Right above it, it says distribution, B-I-S-T-R. That's what we're accessing, is what's in blue here. And I want the second option, normal CDF. All right. And this now allows me to enter, well, let me go past that one, the lower and upper bound along my curve. Now in this case, I only have a lower bound, because I want everything to the right of that point. So I'm going to enter that in as a negative 1.75. And because I technically don't have an upper bound, I'm just going to put in a number that's unreasonably large to make sure I cover everything. 100,000, it's plenty large. I'm not going to ever get any values that big, but it makes sure that I don't cut off any values. Right? I am using the standard normal curve. That's because we standardized the score. So my mu is 0, sigma is 1. Those are fine. We'll hit enter, and it's going to put the command into the calculator here, and I'll hit enter again, and it does the calculation. And I have the same value that I calculated using table A, 0.95994. This gives me a lot more decimal places because the calculator essentially has a table A form saved inside its memory that goes to much more accurate decimal places. So I've confirmed my solution. I've checked it. The reason we're doing that at this point, doing both kind of sides of the work, doing the calculator and doing it by hand, is to build confidence in what we're doing by hand, right? We want to be able to do this by hand. You might be asked to do this by hand on the AP test, where they'll be like, hey, you need to show that you can figure this out using table A, and by finding the z-score first and doing these things, you know. So you have to be able to do that, and you'll still have your calculator so you can check your work. So that's the first example. What questions do you have? What can I clarify? Okay. All right. Does anyone have any need for this to stay on so they can write anything down? Please raise your hand.
Could you actually explain how you got the lower bound number with
Okay.
the 100?
The 290?
No, the 100,000. When you
Oh,
the
yeah.
larger
So
amount.
yeah. So in the calculator, right? For the upper bound in this case, I don't have an actual upper bound. So with this command, the normal CDF command, I can put in a lower and upper bound. So it'll actually find the area under the normal curve between like standard deviation amounts. Like, so I could have negative 1.75 and positive 1.75, and it would find that proportion. For this problem, there is no upper bound established from the problem. So I just choose a number that's, like I said, unreasonably large to ensure that I'm not losing any accuracy. So it's kind of an arbitrary number, but it's arbitrarily large. Does that answer your question, Esmeralda?
Yeah, it does. Thank you.
You're welcome. All right. So let's look at this second one here. So now we have what percent of Tiger's drives travel between 305 and 325 yards? Right, so now we're looking at our graph. This line is not going to be straight no matter how hard I try, but I'll try. Somewhere over here to like somewhere over here. All right, 305 to 325. All this area here. So we want to know the percent again. So we'll be converting our proportion to a percentage between 305 and 325. Now, as I showed you in the previous one, we can do stuff like this on the calculator. So I'm going to show how we could do that after I do it by hand, because there's a fast way to do it on the calculator without even finding the z-score first. But again, we want to practice the mechanics of doing it by hand, so we will. So first, I need to find the z-score of the lower bound of 305. So we'll do 305 minus 304 divided by 8. That will equal 1/8 to 0.125. The upper bound will be 325 minus 304 divided by 8, which will be 21/8, or 2.675, no, 625, I believe. Yep. All right. So these are our z-scores. For table A. Now, if we look at the graph and what we've shaded, we can know right off the bat that our proportion should be less than 50%, because I'm just to the right of the mean and just inside of 3 standard deviations. If I was just going from the mean to the right, that would be 50%. So my proportion should be less than 50%. So if I get something bigger than 50%, there's an error somewhere. So now we'll pull out table A. And we need the positive side of table A. Now, the first issue that we have here is that I have 3 decimal places for both of these numbers. Table A only accommodates for 2 decimal places, so I have to round. Because the third decimal is a 5, I'm going to choose to round up to use 0.13 and 2.63. Right, and that's what I found on table A already here. We have 0.13, which is 0.5517, and 2.63, which is 0.9957. So we'll use those. .9957 and 0.5517. All right. So these are the proportions from table A that we have. Now, again, these are both to the left of the value we found. So this 0.5517 is the area over to the left here. Right, we have 0.5517. Right, and the 0.9917 is essentially going from here all the way over to the left. I only need this much of it. Right? To get that, I just subtract the 0.5517, that extra part to the left, from the 0.9957 minus 0.5517. And that is 44.4, or 0.444. That's 44.4%. All right. Now this, we're perfectly good just stopping here and saying, okay, well, I found it. We have 44.4%. Excellent. All right. And that's the best we can do with the table A that we have. But we also can use the calculator here. Now, the advantage of the calculator right now is that I don't even need to have it standardized. So I can say, okay, well, I'm going to just use the numbers. I got 305 to 325. The mu is 304. Standard deviation is 8. And we get the proportion based on that normal curve of 0.44592, and so on. So essentially 44.6%. And we would get the same thing if I use the standardized scores and the mu of 0 and standard deviation of 1. So using the calculator, we got essentially 44.6%. This doesn't mean that one is wrong. There are two different methods, and because we had to round the decimal to do it by hand and use table A, we have a slight error. However, it doesn't make it wrong. All right. We would say something was wrong if I was like percentage points off and not just decimal points off. Right. But both of these answers are fine. Any questions? I'm hoping this is making it a little bit more clear on how to use table A and how to use standardized scores. That's my hope. Last one. This problem, we're going in reverse. All right, we're going to be given a proportion, right, of the distribution, and we need to follow that back to an original value from the distribution. So in this example, we have high levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with mean mu equals 170 milligrams cholesterol per deciliter of blood, milligrams per deciliter, and standard deviation sigma equals 30 milligrams per deciliter. It says, what is the first quartile of the distribution of blood cholesterol? Right? It essentially wants to know, what is Q1? Right, from our 5-number summary. Right? Q1 is also known as the 25th percentile, which represents a proportion of 0.25. Now, it's really hard to mark this on the distribution here, on our normal distribution. We know that 170, the mean, is the 50th percentile. So the 25th percentile is going to be to the left of it somewhere, so I'm going to be looking at a negative z-score. That's good to know. All right. So we've got to use table A to find a z-score. So the 0.25 is what I need to find on table A. And I find this on the interior of table A, not on the Z column and row. All right. So we go back up to our negatives. And we see, I've done this already today. So we find 0.25 down here in this, almost the bottom corner. But we come into this situation, we're not going to hit 0.25 exactly on the nose. We're going to be in between two values. We have 0.2483, that is 0.0017 away from 0.25, and 0.2514, that is 0.0014 away from 0.25. Since the 0.2514 is numerically closer to 0.25, that is the number we're going to use. when we trace that back, we get a root decimal of negative 0.6. Too far. And maybe having mouse issues. Blink. The second decimal of 0.07. We get negative 0.67 as the z-score. And so then we go backwards using our formula for finding the z-score to find the original value for the first quartile. So that means we start with negative 0.67 equals x, the value we're looking for, minus 170 divided by 30. We rearrange this equation to solve for x, and we end up with 30 times negative 0.67 plus 170 equals x. And this ends up with 149. So Q1, right, the first quartile is 149.9 milligrams per deciliter. We have to add the unit onto this one to be correct, because we are talking about this specific unit of measure for cholesterol, right? And that's Q1. So we're now going from a proportion back to an original score or original value. All right. What questions do you have? That was our last example for this stuff. Okay. All right. So then, last thing to finish out the chapter. Assessing normality. Come on, there we go. My computer's lagging today. All right. So, why normal? Well, it's useful. The normal distributions provide good models of real data, such as things we've looked at, SAT scores, IQ tests, unemployment rates. They can all be modeled with a normal distribution, which is helpful. We have like predetermined tables and rules and things that always work with normal distributions. That makes it analyzing easier. The distributions of some other variables are usually skewed and therefore distinctly non-normal. Examples of this would be like personal income or lifetime of electronic devices, where those results are typically going to be skewed, which automatically means they're not normal. And we have to use other techniques in analyzing them. It is risky to assume that a distribution is normal without actually inspecting the data first. Right? We need a strategy for determining if a distribution is approximately normal. Right? That's what we're going to do. We're going to look at what that is. It's not that bad. All right. So here's our strategy. Is this normal? First step is going to be plot the data. Make a dot plot, stem plot, histogram, use your calculator, and do one of these things. Your calculator is very good at making histograms. I believe it will also make a dot plot. It's kind of hard to see on the graphing calculator. Stem plot you'd want to do by hand. Then ask yourself, is the distribution symmetric and bell-shaped? If it is not, then it is not a normal distribution. You're done checking. If it is, then we need to do the second step, whether the data follows the 68, 95, 99, 7 rule. It does not need to be exactly the 68, 95, 99, 7 rule, but it needs to be close. All right, so this means you take your set of data, you found the mean, you found the standard deviation, and you find out, okay, how many of my data points fall between one standard deviation of the mean? All right, take that number of things, divide it by the total number of things. Is that about 68% of my data? Same thing for within 2 standard deviations, and then for 3 standard deviations. Are those percentages, are those proportions close to 68, 95, 99, 7? If it is, or well, if it's not, then it's not a normal distribution. It might be symmetric, right? And it might be close to bell-shaped, but it just doesn't quite fit into a normal distribution. If it is, and it's close, again, it doesn't have to be perfect, then we have good evidence that the distribution is close to normal or approximately normal. Right? We're not going to typically have something that is perfectly 100% normal distribution. We're going to have things that are approximately normal, which then allow us to use these tools that work on normal distributions. All right. Does anyone need a moment to write this down? You're still not sure? That's okay. Another way to check for normality is by using probability plots. You will not be asked to explain how to make a probability plot on the AP exam. It is just a tool that you can use to justify something being normal. All right, we can do this on the TI-84 graphing calculator. There are directions in the textbook on page 125, and there's also a video that I have in the class resources for today. You interpret a normal probability plot in the way that if the points on a normal probability plot lie close to a straight line, the data is approximately normal. Systematic from a straight line indicate a non-normal distribution. Outliers appear as points that are far away from the overall pattern. What this looks like on the calculator is, suppose we've put in a set of data. Here's our set of data. Right? And we've been going through our stuff. We're like, okay, well, let's see what this thing looks like. We're going to plot. Make sure it's turned on. Okay. And let's say, okay, let's make our histogram. We have that. We're going to, here's a trick, go to Zoom. And keep going. Zoom stat. It should use the parameters of your list and things to make sure you can actually see your graph. Hit enter. There's my histogram. Doesn't look like the whole thing though. Zoom out a little bit. Yeah, that's good. I've got an equation of a line in here somewhere. That was way too far out, but still. Here's our little histogram. Whee! Now, we can go into the same stat plot. And the last possible option here is a probability plot. We select that one. Make sure that we're still looking at list one. These other two things, data axis, leave it as X, mark, leave it in the one it is, right? And again, we'll go to zoom. Stat plot is the 9th option. There's the plot. This is approximately a line. Not perfect, not exactly, but approximately. All right. So that means we have another piece of evidence to say that that distribution is approximately normal. All right. So, any questions?